This is where we left off last week. We're talking about Maxwell equations. So this is a summary of all the Maxwell equations and the constitutive relations between electric field and the electric flux density, magnetic field intensity, and the magnetic flux density, and then the electric field and the current density. We're going to move on to plane wave propagations. So we're going to apply Maxwell equations to show how electromagnetic wave propagates. For wave propagating in free space, so free space, i.e. is a lossless medium, because in the free space there's no conductivity, so zero, and therefore the current density is equal to zero, because we have here this equation here when the conductivity is equal to zero, therefore we have the current density will be equal to zero. And then the charge density in free space is also equal to zero, and then in free space relative permittivity is equal to 1, and then the relative permeability also equals to 1. And therefore from the first Maxwell equation, originally was the divergence of the electric field is equals to the charge density, but we said that in free space the charge density equals to 0, and therefore the divergence of electric field is also equal to 0. And then the fourth Maxwell equation, the curl of the magnetic flux density will be equals to del D over del T. Okay, originally it was curl of H is equals to J and then we replace the magnetic field intensity H with the magnetic flux density, and then we replace the electric flux density with the electric field, and therefore we have a multiplier here, epsilon naught mu naught, and then J, as we established just now, J is equal to 0. So this is the set of Maxwell equations governing the plane wave propagation in free space. So our equation 25, which I have it here. So if we take curl on both sides of this, okay, we end up with this equation here. So the curl of electric field is equals to minus the curl of the time derivative of the magnetic flux density. And then we can substitute equations 26, which is this equation here, which is the curl of the magnetic flux density, is equals to mu naught epsilon naught, the time derivative of the electric field. So we substitute this for our curl B in this equation. So here become epsilon naught mu naught del E over del T. So what we have is that the curl of B is the first time derivative of the electric field, and then we do another time derivative, we end up with the second order time derivative of the electric field, and that is equals to the curl of E. And here we have a standard vector identity. The curl of a curl is equals to the gradient of a divergent minus the gradient squared. And then we establish that the divergence of the electric field up here is equals to 0, and therefore this is equals to 0. And therefore what we're saying is that this is equals to the negative gradient squared of the electric field. So in other words, we're saying that this is equals to this. We have del squared E equals to epsilon naught mu naught time second order time derivative of the electric field. And this equation 29, is known as the wave equation, or it's also known as the Helmholtz equation of plane wave propagations. And del squared is called the Laplacian operator, and I'm sure you have studied the solution of this equation in your maths related to wave equations. So del squared of E, so E is a vector. A vector has three components, x, y, and z. So we can break them down into their components. So here we are just looking at the x components. So meaning that we have del squared E of x over del x squared plus del squared E of x over del y squared plus del squared E of x over del z squared. And that will be equals to the time derivative of the electric field in the x components. Similarly, we have another two components, one for the y. So we have another one which is the same equation on the top. Instead of E of x, it will be E of y. And then this side here will be E of y, or del E of y del t squared. And then we can do the same thing for the magnetic flux density, and we should end up with another similar equations that look something like this. So what we're getting into is that this wave equations will have a unique solutions that give you the electric field will be equals to E naught in the x directions times E exponential j omega t minus kz. So this is the solutions to this equation here. And then this is the solutions for these equations for the magnetic flux density. What it tells you is that the wave is propagating in free space, is propagating in the z direction. So the wave is traveling in the z direction. It has a components of electric field in the x direction. And you will have a magnetic flux density components in the y direction. So if you were to draw it out, this is how the wave going to look like. Okay, so the wave is propagating, if the wave is propagating in the z directions, if you have an electric field in the x directions, and then the magnetic field in the y directions. So wave propagating in z directions, E field in the horizontal directions, and then H field or V field in the vertical directions. And they are always perpendicular to each other. So the electric field, the magnetic field or the magnetic flux density, and the direction of propagations is always perpendicular to each other. You can see that the direction of propagation in the z directions, the electric field in the x directions, and then the magnetic flux density in the y directions. And this is known as transverse electromagnetic wave, or in short, it's called TEM wave, transverse electromagnetic. So which means that the electric field and the magnetic field and the direction of propagation are all perpendicular to each other, or 90 degrees to each other. And this is for the wave propagating in the positive z directions. And we can define a vector known as a pointing vector, P, which is equals to 1 over mu naught, E cross product with B, or E cross product with H. Because we know that okay, so what this tells you is that the cross product of E and H tells you the directions of the propagations, and it tells you where the power flow of this wave. So if I have a wave, electric field in these directions, magnetic field in these directions, and then if you do a cross product of E with H, you find that P will be in the Z directions, and that is the directions of the wave flow, or the power of the wave flowing. Very important equations. It relates the electric field with the magnetic field, and it tells you the directions of the power flow of the wave. I put it in a red rectangular to show you that this is a very important equations for wave propagations. And the parameters k is known as the wave number, and k is equals to 2 pi over lambda. Okay, k is equals to 2 pi over lambda. So it's called the wave number of the wave propagating. And then another important parameter called the velocity, the phase velocity of the wave. And that is equals to omega over k. K is the wave number that we defined just now. We know that omega is equals to 2 pi f. And then if we substitute our omega with this equation k here, we end up with the phase velocity of a plane wave in free space is equals to 1 over square root epsilon naught mu naught. And if you put in the constants of epsilon naught and mu naught, you find that will be approximately equals to 3 times 10 to the 8 and has a units of meter per second. And that equals to the speed of light. Okay, 1 over square root of epsilon naught mu naught is equals to c, which is the speed of light. And that is approximately equals to 2.99 or approximately equals to 3 times 10 to the 8. Okay, so that tells you that the phase velocity of the wave, or in other words, it tells you the speed of the wave propagating in free space. And if we take the electric field divided by the magnetic flux density, you find that that is equals to 1 over epsilon naught mu naught, and that is also equals to c, which is the speed of light. But if you take E divided by h, and that is equals to the square root of epsilon naught over mu naught over epsilon naught, and that is roughly equals to 377 ohms. So normally we equate this to 377 ohms. And this is known as the impedance or the characteristic impedance of free space. It has a units of ohms. This is the impedance of free space. And this is an important parameter because it determines how the wave transmits and how the wave reflects when it hits a different plane or different medium when the wave propagating. So that is how wave propagating. If it's propagating in the plus z directions, you have an electric field in the x directions and a magnetic field in the y direction. And then it propagates at a speed of light, and then it has an impedance of 377 ohms. Maxwell equations, we can write them in a phasor form. So previously we showed that this is our Maxwell equations. Okay, so this is in derivative form. So your B and E in equation 25, 26 is in the time derivative. We can make this into a phasor form. Okay, just now we said that the solutions to the wave propagating is equals to E in the x directions that has exponential j omega t minus kz. So if we take the time derivative of this equation 31a, okay, so if we take the time derivative with respect to t, this will become j omega e naught unit vector x exponential j omega t minus kz. So this part of my equations is my E. Okay, you can see that this is E unit vector in the x direction exponential term, and this is exactly the same as this. So the time derivative of E is equals to j omega E. Similarly, we do the same for B. The time derivative of B is equals to j omega B. And therefore, if we substitute that back into Maxwell equations, we can set that the curl of E is equals to minus j omega mu naught h. And then the curl of H is equals to, you have your J plus, which is your current density, plus j omega epsilon r epsilon naught E. Okay, previously this is, so this term here is, and then we have our D is equals to epsilon r epsilon naught E, and this is simply equals to the derivative, time derivative, is just multiplied by j omega, and then you have epsilon r epsilon naught E. So originally this is equals to And time derivative of b is simply multiplied by j omega. And I think you probably learned that in maths as well, in Laplace transform. Okay, so your Laplace operator is s is j omega, and that is your time derivative. We can rewrite Maxwell equations, especially equation 3 and equation 4, the curl of E and the curl of H, which is equals to curl of E minus j omega mu naught H, and then the curl of H is j plus j omega epsilon r epsilon naught E. As a concluding remarks for these Maxwell equations, so if the wave is propagating in a dielectric medium, then the wave will slow down by a factor of square root of epsilon r. So in free space, we are propagating at c, which is the speed of light. If it's in a dielectric medium, then the phase velocity will be equal to c divided by epsilon r. Okay, it reduced by a factor of square root of epsilon r. Or in other words, Vp will be equals to 1 square root epsilon r epsilon naught mu naught. Okay, originally speed of light is 1 over square root epsilon naught mu naught. So if it's a dielectric materials, epsilon naught become epsilon r epsilon naught. For fixed frequency, this result is an increased wavelength inside the dielectrics. Okay, so the wavelength increases as well, and then it results in refractive or refractions effects when the wave propagating through a different medium. The reason why, I'm sure you know this, okay, you probably studied this in science. If you have a glass of water, you put a spoon, the spoon looks something like this. It's bent. Yep. And this is because of this phenomena, because of the wave propagating at different speeds in the water. And this is called refraction.